Yes, sorry for the delay. Uh, let us start. Do you have any questions about the last times, about some problems? Hmm? Ah, okay. Hmm? Uh, okay, so then let us continue. The last time we studied how to solve the equation, mm, the wave equation with some source. And we found that if we write it in the Fourier image, it becomes minus omega squared plus k squared f tilde equals to u tilde equals to f tilde, and then we solved this equation by saying that u tilde equals to 1 over minus omega squared plus k squared f tilde. So this can be called g tilde, the Fourier image of the gain function. And then u in terms of f can be written as u equals to integral of g of x minus x prime t minus t prime f of x prime t prime dx prime dt prime. So this is called convolution. And we were also computing this. We were also computing this g of x and t. Or maybe t and x, because I usually write t first. X minus x prime. This. So this g of x and t was the integral d omega over 2 pi dk over 2 pi. So minus omega squared plus k squared. And we had to choose how to we had to choose what to do with this poles in the integral. Minus absolute value of k, e to minus I omega t plus I kx, t and x, minus omega t plus I kx. And this. And there was this picture was posed at absolute value of k and minus absolute value of k, and our decision was the following: this integral should vanish for negative t's, so the contour should so we'll should be able to close this contour for negative t's in the so if t is negative, we can close this contour in the upper half plane. So it means that and it should not contain poles. So the answer would that contour should be of this form. But so this is the integration contour, and this integration contour is here. So we obtain some answer integrated it, and finally the result was that it is 1/2 Heaviside theta of t times Heaviside theta of mm, x plus t minus Heaviside theta of x minus t, something like this. And now I want to first say what is the difference between different ways to close on this contour, like what corresponds to the residue at this point. So let us look at this. So if, for example, we decide to take some contour which is just a residue, let us call this some CK. For example, let us choose such a contour like this, CK. So and try to compute the integral around this point. So integral around ck d omega over 2 pi, integral in dk over 2 pi of this expression. Is up to some factor well, maybe we can even compute this factor precisely. So it is minus omega minus k, omega plus k. So it will be 2 pi I times well, integral around the point omega equals to k. Better try it in this way. So we need to compute the residue at this point. So we write 2 pi I, then we should also substitute everywhere omega equals to k, and we get ndk over 2 pi I 1 over minus 1 over 2k e to minus I, well, let us write it like I k x minus t. So we see that this integral becomes immediately a function of, so it is some function of f minus of x minus t. So this contributions from poles, if we decide to write them, will correspond to some solution of the homogeneous equations. So in principle, we can write a solution of a homogeneous equation also as a Fourier integral, but it is it is not very useful, but can be done. So let me maybe formulate it more precisely. Suppose that we have some equation how to denote this. What is denoted by letter D? We have some operator D which depends on D x dx 1 dx n. And we want to find homogeneous, we want to find first solutions of this equation itself, and second, a solution or a solution of the homogeneous equation. Oh, first let's think about the homogeneous equation. So we have some operator that depends on these derivatives. And we have this equation. So let us say that u is a function of u can be given by some Fourier integral. So n or well, so dk dnk over 2 pi to the power n e to I kx u tilde of k u of x. So if you substitute it to this equation, we get what? We get the statement that integral dnk d over 2 pi to the n d is which is a function of k times u tilde of k equals to 0. So it tells us maybe I yes, because it is standard normalization of the Fourier integral. Like any momentum should be divided by 2 pi. So now each derivative operator acts on this exponential and turns into ik. So right. So it means that if we take u tilde of k non-zero on this set when d of ik is 0, then it will be a solution because it is a product of something of some 0 times something non-zero. So we can say that this u tilde of k is proportional to the delta function. So it is some function of k, yeah, f of k times times the delta function of d of ik. And so this integral for u can be written as u of x is the integral over the set when d of k is 0, d of k equals to 0, some volume element. It doesn't matter which precise dv, because in any case we are multiplied by an arbitrary function f of k and multiply by e to the ikx. So example of such phenomenon. So, for example, let us have a three-dimensional wave equation. minus dx squared minus dy squared minus dz squared. U equals to 0. So in this case, our equation will be omega squared minus kx squared minus k y squared minus k z squared equals to 0. So omega equals to plus minus absolute value of k. And solution of the homogeneous equation in this case can be written as the integral of so this u. Yeah, so this u can be written as the integral d3k over 2 pi cubed e to minus I absolute value of k t plus I k x some f plus of k, big f, doesn't matter, plus the same integral for another solution. So this is something that is parameterized by a function or two functions of a three-dimensional vector. And in a one-dimensional case, the difference was that this integral was one-dimensional, and the statement was that arbitrary solution of this equation is a combination of functions of t plus x and t minus x, right? So in 1D, or 1 plus 1, because there is also a time. So in this case, it will be integral over dk over 2 pi e to minus I k t minus x f plus of k plus integral dk over 2 pi to maybe x minus t. And what is written here, just the just arbitrary function of x minus t written as its Fourier transform, and the arbitrary function of x plus t. So the point is that if this operator has zeros for a real case, then the equation has a good solution with zero right hand side. And no, there is also a question what happens if you put here plus and we have solutions for complex k. But and the answer is that such solutions will grow at infinity, and people usually exclude this because, for example, first, they're usually unphysical, and second, it is not a very good to define Fourier transforms of such functions, because the integrals will be just divergent, and there is no way to regularize them, to make them convergent. So, are there any questions about this? Hmm? Mhm. But it's just a matter of convention, or like in programming you have labeled unnamed variables and positional variables. So here I just decided to make everything consistent. So time is. Oh, but what do you mean by a linear? It is just some function. And it should be we should take convolution in both variables. Mhm. So. Mhm. Yes, or that one also, dt squared minus dx squared. So, mhm. But this also works not only for quadratic expressions. We can put here arbitrary polynomial, or maybe even some other function, not necessarily polynomial. So. Mm. Uh, because when we act with a derivative operator on the exponential, it gives ik. Okay. Yes. Yes. Mm, mm, mm. Well, I also wanted to show some a very simple example of this phenomenon, uh, uh, and about this possible choices of contours. So suppose that we want to solve an equation ut equals to f, right? Ut of t uh, equals to f of t. And we try to use this technique. So we say that u so minus I omega u tilde of omega equals to f tilde of omega. And so then u tilde of omega is I over omega f tilde of omega, and we can say that it is this is a green function g of g tilde of omega, and we need to compute the Fourier transform of this green function. G of t is equal to the integral d omega over omega e to minus I omega t. Okay, it is just e to minus I omega t. And let us say that this green function depends on the contour. So let us write this subscript c. On integral is over c. And let us consider the following contours. So this will be C up. Well, just two contours would be enough. Hmm? Yes, yes. Thanks. And I also forgot the factor of I. So it isn't even there. So there is there are two contours of this kind. So let us compute these green functions. So G that corresponds to this upper contour is equal to what? So the first question is when so it should vanish for some value of t, and the question is for which value does it vanish? For positive or for negative t? Yes. So we have this contour which goes above 0, and the integrand is in this one. Hmm? Do you remember the logic? So we should look at this exponential and say that let us check what happens for a positive t. Yes. For positive t, this is just some positive number, and we are interested basically if we can close this contour in the upper half plane so that it does not contain this pole. And to be able to close it there, we should know that argument of the exponential goes to minus infinity when we go to plus I infinity in omega plane. So this is in the omega plane. When omega goes to plus I infinity, this minus I omega is some positive number, and it goes to plus infinity. So it is positive. So this one should be negative. So that this expression goes to zero. Is it clear? So we can draw this contour in the upper. We can close this contour in the upper half plane in the case when t is less than zero. Right. So in this case, it is kind of I infinity times minus I is just infinity times something negative is minus infinity. So all this so this exponential goes to zero on this contour. Mm. And so contribution from this contour, if it is infinitely far away, it goes to zero, and we can say that original integral equals to original integral plus this contribution from infinitely distant contour, which is zero, because this contour, because the value of this function goes to zero on this contour. It's on one side. On the other side, we can deform this contour just to a point, because there are no singularities of function here. So otherwise, it would give a sum of residues. Right? For example, in this case, this contour will contain this residue at point zero. So shall I write it in more detail, or is it already clear? Mm.
The procedure is clear, but precisely the residual on the from that singularity, personally, I instantly I can't find it.
But
Maybe I understand that the contribution, the radial contribution goes to zero, that you before go to zero, but then we have the little so the contribution, the result contribution of.
no, we don't have it because the picture looks like this. We have original. So suppose that. So we are computing the integral d omega over omega, d omega, well, d omega over 2 pi I over omega e to minus I omega t. And let us say that t is greater than zero. Mm. So we draw this. So when t is so t is greater than zero, and therefore minus I omega. So if omega equals to IR and R goes to infinity, uh, well, plus maybe something plus small r. So minus I omega t equals to no, let us say that t is negative because we wanted to consider first on this situation. T is negative, minus I omega t equals to r minus I r times t. So maybe better to write e to minus I omega t equals to e to this, and this goes to 0 at the rate e to r times t. So it goes to 0 exponentially fast. So we can now draw a picture, draw some pictures. So our original integral was this. Then it equals, or maybe without this coordinate axis. Oh, let me remove them. So our integral is on this. Then we can just add this contour at infinity. This is some IR. So contribution from this contour is 0. But then at the next step, we say that this function is holomorphic inside the it's holomorphic everywhere. So we can write that this is our original integration line, and then we just start moving these contours to the upper half plane, then uh, move it even higher, and finally shrink to some integral around some point, so it will be just 0. So it equals to 0. The crucial thing is that there are no singularities inside this contour, so we can shrink it to a point. But this argument is clear that if a function is holomorphic, then we can deform contours, right? Because oh, by the way, do you know what is Dram differential or not yet? Do you know what Dram differential is or not yet? Or external differential? Yeah, yes, a differential of a differential form. Like, hmm? Yes, yes, of course. Like, oh. Okay, probably then.
Maybe the exact formula of the differential is yeah, of the differential form that we have a function that is known in every point, but a non-differential is that function that cannot the variation
No, it sounds strange because no, I don't understand the definition, and this is something from analysis, and I think, but I'm talking about the differential geometry. Did you see the formula for the differential form, or the formula of this kind? D omega is sum over from 1 over 1 to n dx dxi wedge d omega over dx I. Did you see something like this? Okay. Ah, okay. But probably you'll see it later in geometry. Uh, uh, because I just wanted to say that if we work with objects like so, and well, maybe I'll just say a few words and you'll see it somewhere later. So this it's called Dram differential, and these objects with wedges instead of tensor products are skew-symmetric forms. And this is useful, for example, because we can write all this Strahatsky-Rouse-Stokes theorem, all this stuff as a single formula, that integral over some domain D of external differential of form is the integral around the boundary of this domain D of the form itself. And if we do this for if we do this for homomorphic and maybe not necessarily homomorphic functions, then this Dram differential of a function dz f of z, probably z bar, will read as dz bar wedge d dz d d bar df over dz bar. So if a function is homomorphic, if it does not depend on z bar, then it will equal to 0, and it means that contour integral, so if df in dz bar equals to 0, then integral over over the boundary of some domain of this dz f of z bar will equal to the integral over the internals of this domain. Mm, mm. And it will equal to 0. So I just wrote it in a case for the in case when you start learning about these differential forms, then you can remember that this all this complex analysis techniques about deformations of contours is actually can actually be formulated this way. So
Okay, so
so
personally, we solved in past we solved similar exercises, but without speaking about the differential form.
mhm. I'm just saying that it can be reformulated this way. So we can say that if a function is homomorphic, then this form is closed. So it is. So this is 0. But let us maybe come back to this. So did I explain about this integral or not yet? so, so uh, so we know that for negative time, this uh, for negative time, this function vanishes. So it is proportional to heaviside theta of t. And by the way, I forgot to put this symbol because there are other theta functions, in a sense elliptic functions, and one should not miss them. Okay. So we know that this function vanishes for negative time, uh, and we write it explicitly. And the question is, what happens for positive time? So in that case, we can close this contour in the opposite direction. So what will we get in that case?
So the path is equal to before, but opposite.
So no, the integration path is the same. The question is how to complete it, so how to close it. And in that case, this exponential goes to zero on in the opposite direction. So when omega goes to minus infinity, so we can close it in the same way. But what will we get as a result? So, hmm? Yes. Yeah. Hmm? Oh, yes, for when t is positive, so what happens? Hmm. So, what will happen instead of in this picture? So, let me draw the same picture here. So, its contribution from this part is goes to zero. So it's for t greater than zero, and now we can shrink it like this. So and finally to the integral just around this point. Right? Well, almost. So it's going in the clockwise direction. So when it is clockwise, then what happens? dz over z is d omega over omega equals so when it is clockwise, then it is integral from 0 to 2 pi d e to minus I phi over e to minus I phi. So it is the integral from 0 to 2 pi uh, minus I d phi. So it is minus 2 pi I. So and to get mm, mm, so this if this integral goes in the clockwise direction. If it is in the clockwise direction, in the anti-clockwise direction, it would be 2 pi I. In this case, it is minus 2 pi I. So, so what do we get? The result. Mhm. Hmm? Yes, yes. Mhm. But but you can ask me for if you need some formula because actually, mm, oh, oh maybe because in principle everything is written. Oh wait, oh I can think. But can you show? Hmm? Uh, and this is how, but why 1/2 pi is squared?
1/i/2 pi was from this integral,
Uh,
and then multiplied by
no,
this
but
constant.
no, why 1/2 pi? Because it is a integral. So how to remember this? It is integral over some angle. So this integral d omega over omega in the clockwise direction is minus 2 pi. Because it.
Computed the integral with the exponential too.
Yes, but what is the contribution from the exponential? Omega is close to 0. So 1 over omega times the exponential of minus I omega t is, we need to write Laurent series of this function. So it is 1 over omega minus I t minus omega over 2t squared plus and so on. But the main point is that this function is regular at omega equals to 0. So the only term that can contribute to this integral comes from the leading part. So this exponential can be just replaced by 1 by its value at omega equals to 0. So, hmm? so if it was 1 over omega squared, then we would need to expand this exponential up to second order, well, up to the first order in t to get to find coefficient in front of 1 over omega. Mm. So. Mm. Oh, but well, let me no. Mm, so we are computing this integral. So now it is integral around 0 in the clockwise direction. D omega over 2 pi I over omega e2 minus I omega t. It is so this exponential can be replaced by 1 because of this argument, because it is multiplied by first order pole, and it does not affect. So all the other terms in this expansion do not affect the answer. So so it will be integral d omega over 2 pi I over omega. So, and we know how to compute the integral of the omega over omega. So we just do this. Minus 2 pi, minus 2 pi I, times what we had originally, I over 2 pi. So it equals to 1. Right? So if it was 1 over omega squared here, then well, let us see how it works in that case. Integral d omega over 2 pi, well, d omega over omega, just d omega over omega squared e to minus I omega t. So in this case, it will be the integral d omega, it will be d omega, well, maybe in the clockwise direction for simplicity. D omega 1 over omega squared minus it over omega plus plus something. So the question is, what will we get in this case? What will be the value of this integral? What is the value of the first integral? So integration contour is some loop around 0. No, not very big, but here it can be just any loop. Can you imagine that you compute this integral as a first indefinite integral and then try to substitute the limits of integration? So what will you get in this case? Maybe I can erase in this picture. Hmm?
The function 1 over omega square as a formula of 2, 0. So there's a formula to compute the value of the residue imposing 0. I would use this one plus the residue theorem. That's what I would
What is the answer for this part of the integral?
I can't remember the formula.
But you should not remember the formulas. You should remember some kind of common sense, like how to obtain them. Some arguments which give this formula. So we have this function
The derivative
of 1 over omega. Yes, of course. So it is yeah. So it is a derivative of 1 over omega. But if you try to do this with 1 over omega, which function will you get? Minus it. So it will be derivative of what? Yes, yes. And so basically, if you have any power except for 0, it will be some power of omega, d of power of omega. So this integral will be, so now it's the integral of some derivative. we need to compute, so it equals to 1 over omega. So if we imagine that this is some integral from a to b, then it equals to 1 over omega, minus 1 over omega, minus 1 over omega, minus I t, logarithm of omega, integral from, well, let us put some higher coefficients, like minus t squared over 2 here. So then there will be minus t squared over 2 d omega. So it will be this expression minus t squared over 2 omega, and this is in principle plus something else, and this integral is from a to b, from some a to b. But actually, this a and b are the same variables. It is kind of a and a times e to the 2 pi I. So all functions that are different from logarithm will just coincide on these two limits. So these integrals will vanish, and the only function which can contribute to this logarithm of omega. But logarithm is a multi-valued function because if we say that let's say that it is indifferent parameterization, it is minus it logarithm of some r times e to I phi. We say that omega equals to r e to I phi, or a. Maybe let us say that it is r. Here is r. And for example, r is real, for simplicity. So and this is from 0 to 2 pi. So, and now logarithm of this will be just so minus I t logarithm of r plus I phi from 0 to 2 pi. So it's phi equals to 0, phi equals to 2 pi. So and so so is it clear that this parameterization parameterizes a circle of radius r in the complex plane, right? Mm-hmm. Yes. So, and logarithm of complex number is just the logarithm of any other number. It's logarithm of r plus I phi, and then we need to compute difference of this function at phi equals to 2 pi and phi equals to 0. So, what will be the answer here?
And you did 2 pi t.
Yes. So this is the value of this integral around zero in the counterclockwise direction. So mm, okay, so the point is that when we want to compute residue, we should always expand the function around this point where we want to compute it, and take the coefficient in front of 1 over omega multiplied by 2 pi I or minus 2 pi I if it is in the clockwise direction, because all other terms do not contribute because they are differentials of some functions. And this is a 1 over omega is differential of a multivalued function. So, okay, so, okay, so the answer is actually written here. So that's all. And can you just say immediately what is the value of another function?
Would it be theta of minus?
And also with some other modification. What modification if you look at this contour? Hmm?
Minus theta
Yes, yes.
Because of the clockwise
Here anti-clockwise. Yes, yes. Okay. Yes. So there are these gain functions, and let us use them to write a solution. So there are two options. Well, maybe. Well, let us write it here. So we have one solution like u up. Is a convolution of j of this gain function j up with f. So it is by definition of t. It is by definition the integral of g g up of t minus t prime f of t prime dt prime from minus infinity to plus infinity. So mm, now what happens with this integral? When t goes to plus infinity, this gain function goes to zero, and it is zero until t prime equals to t. And if t goes to minus infinity, it's always zero. It's always one. All right. So this integral is the integral from minus infinity to t g well of f of t prime dt prime. Right. And what will we get for g for u down? Yes, it's kind of, the same. And what will we get in the answer?
So the integral goes to 0 for t prime that goes to minus infinity.
Yes.
Then for t prime that goes to plus infinity, it's equal to the integral from t to plus infinity.
Yes.
Minus f prime of t prime.
Well, f of t prime. Just. Yes. So and and if we have this, I think it is easy to see that they actually solve our equation, right? And the difference between these two solutions is just some number. It does not depend on t actually. It should be, and it is the integral of f of t prime from minus infinity to plus infinity. So so here is this example that. Uh, that different green functions correspond to different solutions. So one green function depends on f in all previous moments. Another green function depends on f in all future moments. So is it okay? So let us also try to consider. So, so can I go further? Let us also consider some other example, a small modification of this one. Let us write ut equals to f of t. Ut of t equals to f of t. Ut plus gamma u of t equals to f of t. Uh, so let us first try to solve this equation. So what should we do? We should say that u is u of t is e to minus gamma t u1 of t. And now substitute it here and get that e to minus gamma t u1 prime of t equals to f of t. So u1 prime of t is e to gamma t. Maybe we can write u1 of t equals to the integral e to gamma t f of t from 0 to plus infinity, from minus infinity to t, one option. Or we can write equivalently, so either this, or you can also choose some other point. So you can write integral from plus infinity to t e to gamma t f of t dt. So something like this. And we see that in principle one solution is better than the other one uh, we have no guarantee that this integral is convergent. Well, in principle, we don't have guarantee that this first integral is convergent because it depends on the asymptotics of f. But if we believe that f has a Fourier transform, then it goes to zero at infinity reasonably fast. In this sense, the first integral looks better. But let us see what happens if we try to compute to find this gain function using the Fourier transform. Right. So in this case, we'll have that this gain function of t is the integral from minus infinity to plus infinity d omega over 2 pi e to the minus I omega t. And what should we put here? Yes, so and gamma is of course here because it was in the equation. What else?
Gamma minus the omega.
Mm-hmm. Yes, thanks. Mm. And what is the value of this integral? So now you see that this singularity is in the upper half plane. So mm, there is this I gamma. So it moved there without our assistance. It is just there at the very beginning. So let us look at this picture. So sorry. Uh, no, it, no. What did I write? It is in the lower half plane. I, I can't solve equations. So it is here. Minus I gamma. So how to compute this integral and what will we get?
So we can draw a path
Hmm?
to the down to the plane.
Yes.
See, see,
Mm.
and consider the residual to minus gamma.
Yes. So it's basically the situation drawn on the first picture, but this pole is now not at zero, and we don't need to deform the contour. It just goes down, and yes. So what changes here? So we'll have the same theta function in the prefactor.
So we get another case of theta function, but
Hmm? Mhm. So so this argument about possibility to go the contour stays. It does not depend on all the factors. It's just about the exponential. So here it's theta have a side of
Because the pole is not in the beside the contour. It's like in the contour upwards.
yes, yes. So when t is positive, then this exponential goes to zero when omega goes to plus infinity, and so we don't have this control. And what changes? What else changes? What changes in the residue computation? So there we expanded this exponential around zero, and the only important part was its value at zero. And what changes?
Over gamma and not one.
No, but here, no, here we compute the residue in omega. So we should shift omega to this variable.
so maybe it is similar to the first case. We have simply a shift between for the singularity between omega and minus gamma e. So
Yes.
I think
So
cioè, in questa situazione citato, visto che cioè,
so
questo spostarsi adesso è
so this now should be expanded not around zero, but around minus I gamma, right? And and the leading term is the e to minus gamma t. So and this is what contributes to the residue. So e to minus gamma t. So so now if we use this again function to write a solution, then what should change? We should write this integral, but with this prefactor. So u of t will equal to integral from minus infinity to t e to minus gamma t minus t prime f of t prime dt prime.
gamma t distance depending on the variable. Sì, dello stesso non c'è questo. Ok,
Okay. Mhm.
esatto.
Oh,
Oh, okay, so this, in this case, this method with Fourier transform gives one particular gain function. So in principle, this equation can have many gain functions. It can contains a solution of the homogeneous equation. But the problem with solution of the homogeneous equation is it is exponential and it grows at one of the infinities. The gain function is clever and says that if you write something like this in the answer, it will be a function that does not have a Fourier transform. And uh, uh, so this is why we get only one answer, and namely we get some function which decays uh, at the infinity reasonably fast. So.
So, if I understand correctly, there is no Fourier transform of the function inside of the integral.
No, I'm saying that if we take a function e to gamma t and try to compute its Fourier transform, it will not exist.
Oh, okay.
So it will be a solution of the homogeneous problem. So we will need to write some. So maybe we. Oh, if it is some oscillating exponential e to I omega t, we can say that it is e to I omega t or I gamma t can be written as the integral from minus infinity to plus infinity d omega delta of omega plus gamma e to minus I omega t. So we can kind of Fourier transform this function, or we can write the same formula for delta function, because it corresponds to some delta function on the real line. But for a real exponential, we will need to put this. We will need to write some function that does not exist. So on one side we need to integrate over the real line. On the other side we will need to take a value of this exponential at some imaginary point. So to describe this, we will need to modify the Fourier transform to say that it's for functions on some shifted domain in the complex plane. So. Uh, so So this experiment shows, in principle, not very good because integrals naively do not converge. We get some generalized functions as a result, but we can deal with them. But real exponentials are not in this class, and so they don't appear in the formulas for the gain functions. So we get just one answer. Okay, so.
Just a question. So we can think about the exp e gamma I gamma t like a function that is not a good test function to make a Fourier transform because in a similar case in complex analysis we cannot do the Fourier transform of a function that are not in L2 of
Yes,
okay.
yes.
Okay.
L1. So to compute Fourier transform, it's sufficient that it is in L1, so that integral converges. But
Okay.
people ask for L2. So it's definitely not a test function. Test functions which people use are usually at least exponentially decaying or better with compact support.
Okay.
Mm, mm, But, but in this case, I remember we could multiply it by some epsilon absolute value of t, and then this integral becomes convergent. So here we will need to put something like mm, delta epsilon, with delta epsilon equals to 1 over pi epsilon over x squared plus epsilon squared. So in this case, we will get this delta sequence, but if it is real exponential, then this small modification that can be sent to zero just does not exist, because it should be something, it should be some substantial modification of a function which will affect the integral. So. Okay. Uh, Let us discuss. So can we go further? So let us discuss the following question. We obtain this gain function as something that appears in the as a result of a solution of this equation in the Fourier space. But let us try to ask what about the definition of gain function. Namely, let us ask what equation is solved by the gain function. Uh, I remember that gain function appeared. So where is it written? Maybe. Yeah. So a gain function appears when we invert the left-hand side of equation. So we have some a differential operator of this d's dn action f or action u equals f. And we write that g that u equals the u tilde is 1 over d of ik1 d of ik f tilde. So and this is the Fourier transform of the gain function. But if we want to get the gain function itself, um, it is clear that we can just say that f tilde equals to 1. So if f tilde equals to 1, then this u tilde equals to the gain function. But the question is, what is this function f tilde? What is the function f if f tilde equals to 1? The Fourier transform of a function equals to 1. in a sense, how to recover function from its Fourier transform, or maybe it's better to think in the opposite direction. So we know that a Fourier transform of our function, Fourier transform that depends on k, is given by definition, so d n x e to the minus 2 pi minus ik x f of x, and we know that f tilde of k equals to 1. And we ask what is f of x, so that it is 1.
Maybe 2 pi delta.
No, but no, f tilde of k is 1. I'm asking about f of x.
Oh.
So if it was 1 in the right hand side, then yes, it would be a correct answer. But But you can just try different functions. So you thought that there should be some delta function. So what happens if you substitute delta function multiplied by something? What will be the value of this integral? What will the delta function do when you try to integrate it with something?
It send the function in the argument of the delta.
Yes. So no. So what the argument of delta?
In this case, or
Oh, so what is the integral of some phi of x delta of x dx?
is p of 0.
Yes.
So f of x can be delta of 0.
What is delta of 0?
Um,
No. What? Delta of 0 is not defined. It's in infinity.
um,
Like here, it's 1 over epsilon. What? What is the problem? Just to guess the answer. Like. What isn't clear? I can ask, what can you choose here? What are the possible options?
Okay. Are we integrating in any dimension?
Yes, but
Sorry, I don't read it before.
but it doesn't matter. So yeah, so the answer will be almost the same. For example, this formula is also related because if you want to get 1, you can substitute gamma equals to 1, gamma equals to 0. Then this oscillating exponential will become just 1. And it's a phenomenon of the same type. But, what is precisely unclear? Like what are the options you are checking? So so we have a formula like this, and we have a formula like this with the unknown right-hand side. Why can't we guess what is on the right-hand side? So, so the hint is that this one is just the value of this exponential at 0. So, hmm? Uh, no, so once again, we had this phenomenon that we can express exponential of I gamma t as the integral in d omega with such a daughter function, which gives contribution from a single point when omega equals to minus gamma, right? So this integral gives, in particular, if we set gamma equals to 0, left hand side and the left hand side will be 1, and the right hand side will be exponential of 0, so 1. It will be so delta function of omega is for an image of 1. So in other words, we can write that 1 equals to minus integral from minus infinity to plus infinity d omega delta of omega e to minus I omega t. And now we know that Fourier image of this function is 1, and I'm asking what is the function itself. What should we Fourier transform to get 1? I don't know. When I wrote the answer, is it clear that the Fourier transform of this is actually one? So, so okay, not product, but just. So. We can write it as a product of one-dimensional delta functions if we want to understand this integral as an iterated integral. Or we can just leave this symbols saying that we should integrate as a delta function with this volume element, and it will give a value of a function at zero. So you can understand it as a multidimensional generalized function.
So, solving by part, we get one from integral on the right.
What by part?
By parts.
No, but what should we integrate by parts? It's, mm,
Okay.
mm. So just all this integral is equal to one because it's a value of this exponential at zero. So, so is it clear or not? Or if not, what is precisely unclear?
So, for the in order in the order of order n.
Mhm.
So you mean derivative?
No. It's I did yes. It's some conflict of notation. No, definition is here. It is a product of delta functions of all components of this vector. So, or if our parentheses are confusing, we can write this. So, integral. So is it fine or not?
So by using, we can see it maybe by using property of the exponential and the factorization of delta, we can have n integrals in n variables. So
Yes.
it is like one integral to n, and it so we get one.
Yes, 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 of course, yes. This product of delta functions integrated with function of n variables just puts all these variables equal to 0, because each integral equals to function computed at the point when this variable is 0. So.
So the problem, I think, is that at first we confused the order of n like a derivative, but it's not n order of derivative, and it's a factorization of that.
Yes, but it's a function of a vector argument. Like how could you take a derivative of the vector argument? This is maybe why this notation does not conflict with derivatives of a one-dimensional vector function. But here the answer is, so it means that this green function so 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 the statement is that green function solves this equation with a delta function on the right hand side. And let us check that it is true in this case, which we have here. So so let us take, for example, this green function, so that is not so trivial. And so we need to check that dt of each theta h of t, e minus gamma t, plus gamma theta h of t e to minus gamma t. So it will equal to dt of theta heaviside of t times e to minus gamma t. And now let us try to compute this integral. So when t is greater than 0 or less than 0, so it equals to 0 when t is different from 0. So is it clear why?
Because of derivative of theta of heaviside of theta heaviside goes to delta of dirac.
Well, we will see it immediately, but it's 0 just because it is either 1 or 0. And
Okay.
yeah, well, it was some jump one step ahead. But if we check what happens at 0, then integral from minus epsilon to plus epsilon of this delta dt t that I have aside e to minus gamma t equals to theta heavy side of t e2 minus gamma t from minus epsilon to plus epsilon plus or minus the integral like from minus epsilon to epsilon theta heavy side e2 minus gamma t. Oh, actually we can plus gamma dt, but this integral is this integral goes to 0. So or we can actually compute both of them. Oh, so the answer is that it is 1. Well, actually we compute both integrals and I see that it is really 1. So it means that this is really really delta function at 0. So it's a delta function of t.
I don't understand the final goal of
Oh, I wanted to show that green functions obtained in such way are actually solutions of the equation with a delta function on the right hand side, and then check it in this particular example. And this is useful knowledge because if we because really if you need to find some green function in some different situation, it might happen that we cannot apply Fourier transform because, for example, we live in some trivial domain. But if we manage to construct a solution of this equation with a delta function, then we win. And usually, so we will see some examples, but usually it works in this way. We solve homogeneous equation in all domain except one point, and then impose the asymptotics around this point, so such that we get a delta function on the right hand side. For example, we know the behavior of the green function in the infinite space where we can compute it exactly, and then ask for this asymptotics in some more complicated problem. For example, if it is a two-dimensional Laplace equation, we know that its green function is in the infinite space is a logarithm. And if you want to find its green function in some trivial domain, we look for a function that has a logarithmic singularity at this particular point and has appropriate boundary conditions. So. And usually, so in some cases, maybe actually in all cases, this result can be recovered from some Fourier transforms, but in general, it is easier to obtain it by solving a equation with boundary conditions, because there are different methods, like conformal maps and so on. And also, well, maybe let us talk let us talk about this next time. But I wanted to say that the fact that this that this equation, this gain function solves the equation with the delta function, allows us to connect different gain functions. For example, um, we can transform this right-hand side into non-trivial boundary into non-trivial initial conditions. Like if you solve the equation with a delta function on the right-hand side, it corresponds to one kick at some point at some moment of time. So it gives a non-trivial initial velocity to points of string, and then we can solve this problem using grand functions for initial conditions. So it is a general situation. Okay. Yeah, so we are out of time. So that. So are there any questions on this? Okay, then maybe thanks for your attention. So, and see you tomorrow.